Thwaites Glacier is still moving, still thinning, and still feeding ice into the Amundsen Sea, but a new result published in late July changes the most obvious way to think about what is happening there. Scientists took 3 ice sheet models and asked an extreme question: what if the ocean stopped melting the floating ice around Thwaites entirely, not slowed, not cooled a little, completely removed as a source of ice shelf melt in the experiment? Thwaites still lost ice. That is the new warning. It is not a forecast that Antarctica's so-called Doomsday Glacier will collapse tomorrow, this decade, or on any exact date. The authors explicitly say their experiment is not meant to predict the glacier's future. Instead, it tests something more basic and in some ways more unsettling: how much of the loss already underway is a response to changes that happened decades ago, and how easy that loss would be to reverse. The answer was very different for 2 neighboring glaciers. Pine Island Glacier thickened and began to advance in the zero-melt experiments. Thwaites did not. Across all 3 models, Thwaites continued to lose mass for the full 150-year simulations, although the rate declined with time. The main grounding line did not significantly return toward its earlier position. The researchers concluded that part of the glacier's present-day loss is an ongoing adjustment to a historical disturbance, and that simply cooling the ocean would not restore the glacier to its expanded, mid-20th century configuration on policy-relevant timescales. Stay with me because the distinction matters. This does not mean every future meter of retreat is locked in. It does not prove that Thwaites has crossed one single irreversible tipping point from which all collapse is unavoidable. And it does not mean cutting greenhouse gas emissions is useless. The study says none of those things. What it does say is that the glacier has memory. That memory is a physical state, not a metaphor. Ice thickness, the position of the grounding line, the shape of the bed, and the stresses transmitted through floating ice all help determine how the glacier moves today. Once retreat changes, that geometry, removing the original disturbance, does not necessarily put every boundary back where it started. The July experiment was designed to isolate exactly that problem. By setting ocean-driven melting to zero, the researchers created a test that cannot happen in the real ocean, but one that makes the diagnosis cleaner. If the glacier keeps losing mass, after the direct ocean melt forcing is removed, some of the loss must be coming from the glacier's inherited dynamical response rather than from present-day melting alone. That is why the comparison with Pine Island is so revealing. The same extreme experiment produced a much stronger recovery there. While Thwaites remained on a losing trajectory, a glacier this large does not respond to the climate like a puddle responding to a cloud. Once its grounding line moves, once its floating margins weaken, once the geometry of the ice and seabed changes, the system can keep adjusting long after the original push. Thwaites is not merely reacting to today's water temperature. Part of its current motion may still be the delayed consequence of changes that began in the middle of the 20th century. That is why Thwaites has earned such intense attention. It drains a huge sector of the West Antarctic ice sheet and sits on bedrock that is largely below sea level. Much of that bed deepens inland. In simple terms, the farther the grounding line retreats into some parts of the basin, the thicker the ice exposed at the point where it begins to float. That geometry can make retreat difficult to stop once it develops, although the real glacier is far more complicated than any one textbook instability. The numbers explain the scale, but they also need careful framing. A 2026 seismic study reported that since 2002, the Thwaites drainage basin has lost mass at an average rate of about 60 gigatons per year, corresponding to roughly 5% of global mean sea level rise over that period. The glacier alone contains enough ice to raise global sea level by roughly 65 centimeters if it were completely lost. That is a long-term potential, not a near-term forecast. And the larger concern is that Thwaites is connected to a much broader marine-based ice system in West Antarctica. Earlier this year, another study added a different kind of warning. Researchers calibrated 2 independent ice sheet models using satellite observations of how Thwaites' surface elevation has changed over time. The versions that best reproduced observed loss projected much higher mass loss rates in the coming decades, reaching around 180 to 200 gigatons per year by 2067 in those experiments. The modeled thinning spread roughly 100 kilometers inland along a deep trough beneath the glacier. Again, that is a model projection, not a measured future fact. The study itself showed that the answer changed depending on how the models were calibrated, but the important point is that multiple 2026 studies are converging on the same central problem from different directions. Thwaites is already in a state of rapid loss. The geometry beneath it matters enormously, and its future is controlled by more than the temperature of the ocean on any single day. In January and February, scientists physically went after that problem in one of the hardest places on Earth to work. A British Antarctic survey and Korean team drilled roughly a kilometer through the glacier's fast-moving main trunk to reach the ocean below. They temporarily obtained the first direct measurements from beneath that part of Thwaites. The water was relatively warm by Antarctic standards. and the observations showed turbulent conditions capable of driving substantial melting at the ice base. The team had hoped to leave instruments there for 1 or 2 years. The glacier had other plans. The borehole began refreezing, the ice was deforming, and the mooring became stuck during deployment. The equipment was lost inside the ice. In parts of the site, the glacier was moving more than 9 meters per day. That single field operation captures the larger problem. Thwaites is not a clean block of ice sliding over a smooth floor. It is a moving, fractured, water-influenced system interacting with a complicated seabed, a changing ocean, and its own evolving geometry. And in April, scientists published the clearest large-scale seismic picture yet of what lies beneath it. They drove vibroseismic surveys across hundreds of kilometers of the glacier and found a bed that looks nothing like a simple ramp. There are hard ridges with steep upstream-facing slopes. There are sediment-filled basins. There are areas containing widespread subglacial water. One active lake sits above tens of meters of highly porous water-saturated sediment. Some of those features may slow the glacier by increasing resistance. Others may encourage sliding or change how stress is transmitted through the ice. This is where the story becomes more complicated than the phrase Doomsday Glacier suggests. Thwaites has obstacles beneath it. The bed contains ridges that can resist flow, and one 2026 study emphasized that current models do not fully capture this complexity. That uncertainty can work in either direction. A ridge may delay retreat. A water-rich basin may alter basal friction. A deep trough can guide thinning inland. The future depends on which controls dominate as the grounding line migrates. The newly mapped bed also explains why simple labels such as stable or unstable can be misleading. Some elevated rough areas create basal drag and resist fast flow. Between them are lower basins containing sediments and widespread water. Those contrasting patches can change how easily ice slides and how stress is transferred from one part of the glacier to another. A ridge can act as a break for a time, but the effect depends on where the grounding line sits relative to that ridge and what lies farther inland. The 2026 seismic work, therefore, did not produce one clean switch that scientists can point to and call the collapse threshold. It produced a more realistic map of obstacles, weak zones, water-bearing sediments, and slopes that future models must represent if they are going to narrow the range of possible retreat rates. So when the July study removes ocean melting and Thwaites still loses ice, the result is powerful precisely because the real world is not going to remove ocean melting. Zero melt was an intentionally unrealistic test. Even seawater near its freezing point can still melt ice at depth because pressure changes the freezing temperature. The experiment was designed as a diagnostic if the glacier continues to lose mass under an unrealistically favorable ocean condition. Then some portion of that loss must be coming from the glacier's inherited state rather than from present-day ocean heat alone. That inherited state appears to reach back to the middle of the 20th century. Sediment records and reconstructions indicate that Thwaites and neighboring Pine Island Glacier began major retreat during that period after losing contact with important seabed features. For Thwaites, the western part of the system ungrounded from a pinning point around the 1940s or 1950s. Once that happened, the geometry of the glacier changed. The grounding line moved. Floating ice became reorganized. Stress patterns shifted. Decades later, the glacier is still adjusting. The July simulations ask whether an extreme cooling intervention could simply make the old geometry return. For Pine Island, the answer in the models was largely yes, remove the ocean melt, and it thickened enough to advance. For Thwaites, no comparable recovery occurred. That contrast is the heart of the new paper. But there is another crucial boundary. The researchers did not find evidence in those zero-melt runs that Thwaites' losses grew without limit. The loss rate declined. They said, the results are consistent with a historical threshold separating the old expanded state from today's configuration, but determining whether that threshold is a formal tipping point would require a much broader set of stability and reversibility tests. They also stressed that their experiment does not prove all future retreat will be irreversible. That language is not a footnote. It changes how we should understand the warning. The frightening interpretation would be, Thwaites has passed a point of no return, therefore catastrophic collapse is now guaranteed. The evidence does not support that sentence. The stronger, more accurate interpretation is, some future loss from Thwaites appears difficult or impossible to reverse on centennial timescales, even under an extreme reduction in ocean melting, because the glacier is still responding to changes that already happened. How much additional loss occurs, how fast it happens, and how far retreat proceeds remain sensitive to future forcing and to physical details that scientists are still working to constrain. That difference is enormous for coastal planning. Sea level does not need a sudden cinematic collapse to create problems. A glacier can add water gradually for decades and centuries, stacking onto thermal expansion losses from Greenland, other Antarctic glaciers, and mountain glaciers. The rate matters because infrastructure, flood defenses, drainage systems, insurance markets, and coastal ecosystems all have limits on how quickly they can adapt. Thwaites is already contributing to that background rise. The question is how much faster that contribution becomes. This is where the March 2026 model study adds pressure. It found that mass loss from Thwaites has accelerated strongly since the 1990s. When the researchers trained two independent models using observed surface height changes, those models not only matched recent volume loss patterns better, they also projected the largest losses through 2067. The modeled rate by the end of that period was comparable to the current loss from Antarctica as a whole. That projection should not be blended with the July zero melt experiment as if they were the same forecast. They are asking different questions. The March study asks how observations can improve forward projections. The July study asks whether historical retreat can be reversed in an artificial no-melt world. One is about plausible future loss under fixed modeling assumptions. The other is a stress test of reversibility. Together, though, they tell us why scientists are not treating Thwaites as a simple problem of warm water equals melt, cool water equals recovery. The glacier has geometry, it has history, it has internal feedbacks, and it has weak points. One of the most visible weak points is its floating ice. Thwaites has an eastern ice shelf and a western ice tongue, both of which have changed dramatically. Fractures have expanded through parts of the eastern shelf, and previous research has shown that sections of the shelf are approaching the end of their structural life. Satellite observations have documented increasing damage and faster flow in fractured zones. It is tempting to treat the breakup of that floating shelf as the single countdown clock for Thwaites. But that too is too simple. A 2023 modeling study found that complete loss of the Thwaites ice shelf by itself would not substantially change projected mass loss over the following 50 years because the shelf currently provides limited buttressing to the grounded glacier. In other words, dramatic-looking shelf breakup does not automatically translate into an equally dramatic immediate jump in sea level contribution. That may sound reassuring until you understand the larger point. Thwaites does not need one spectacular shelf collapse moment to remain dangerous. Its grounded ice can continue retreating because the deeper problem lies in the interaction among bed geometry, grounding line position, ocean forcing, and the glacier's inherited dynamic state. Think of the grounding line as the moving boundary between ice resting on the continent and ice floating on the sea. Grounded ice contributes to sea level rise when it is transferred into the ocean. Floating ice has already displaced its own weight in water, so its direct melting is not the main sea level problem. Its importance is mechanical and thermal. It can buttress inland ice, and it controls where ocean water reaches the base of the glacier. There is another distinction that matters whenever sea level numbers enter this story. Floating ice is already displacing ocean water, so the breakup of an ice shelf does not by itself add the full sea level equivalent of the grounded glacier behind it. The larger concern is mechanical floating ice can transmit resistance back toward grounded ice, and changes in that resistance can alter how quickly grounded ice is discharged into the ocean. The grounding line is therefore the more consequential boundary. When grounded ice crosses that line and begins to float, ice that was previously supported by the bed has entered the ocean system. This is why scientists watch grounding line retreat, bed slope, ice thickness, and flow speed together rather than treating one spectacular crack at the surface as a complete measure of future sea level rise. At Thwaites, that boundary has been retreating. Warm circumpolar deep water can reach the cavities beneath floating ice and attack the glacier near the grounding zone. Observations have shown that melting is highly uneven. Flat parts of the ice base can experience relatively modest melt because a stable layer of cold, fresh meltwater suppresses heat transfer, yet warm water can penetrate cracks and steep surfaces, producing much stronger local melting in crevasses and terraces. That detail changed the picture several years ago. The glacier was not simply melting fastest wherever the ocean was warmest. Geometry controlled where the heat could do the most damage. The same principle appears beneath the grounded ice. The April seismic survey revealed steep, hard obstacles in large, water-rich sedimentary regions. A hard ridge can act like a break. Water and soft sediment can reduce resistance. An active subglacial lake can drain and refill. No single measurement tells you the fate of the entire glacier. This is why the phrase "what scientists are saying" needs to include disagreement and uncertainty, not just the most alarming number. Some studies suggest Thwaites may be vulnerable to marine ice sheet instability as retreat enters deeper inland terrain. Other analyses find no clear evidence that the present grounding line configuration is already undergoing self-sustaining instability everywhere. Some models produce committed retreat even without ocean melt. Others show that the rate and extent of future loss remains strongly dependent on ocean temperature, model resolution, basal conditions, and the way observations are used to calibrate the system. Those statements are not contradictions. They describe a system with several competing controls and large uncertainties. The new July result does not erase the importance of ocean warming. In the real world, ocean melt is not zero. Warmer water continues to reach the Amundsen Sea sector, and previous modeling has shown that changing glacier geometry can increase melting, even without a change in the broader ocean climate, by exposing more ice to warm water and altering circulation beneath the shelf. The authors of the Zero Melt study make this point explicitly in their conclusion. Some future sea level contribution from Thwaites appears unavoidable on centennial timescales in their experiments, but future ocean temperatures still strongly influence the total rate of loss. Mitigation can therefore change the size and speed of the outcome, even if it cannot rewind the glacier to the way it looked before the middle of the 20th century. The fact that the future is not fixed is not a rhetorical escape hatch. The July study deliberately removed one, forcing to diagnose the system. It did not simulate every possible future climate pathway. Real-world ocean temperatures, circulation, atmospheric warming, snowfall, ice shelf fracture, and the detailed geometry of the bed can all affect how quickly mass is lost. The author's central warning is narrower and in some ways more unsettling. Cooling the ocean alone does not reset Thwaites to its earlier state on the century-scale window they tested. That leaves a large difference between unavoidable loss and total possible loss. The first is a commitment already embedded in the system. The second still depends on what happens next. That is a difficult message because it contains two truths at once. First, some damage appears to be built in. Second, the future is not fixed. If those ideas sound incompatible, picture a car already rolling downhill. Braking may not return the car to the hilltop, but it can still determine whether it crawls, accelerates, or crashes. That analogy is imperfect because a glacier has many moving boundaries and feedbacks, but the decision logic is similar. The inability to fully reverse past change does not mean the amount of future change is predetermined. And that is why scientists keep going back to Thwaites. They drill through a kilometer of moving ice. They lower instruments into black ocean cavities. They tow seismic sources across hundreds of kilometers of frozen surface. Satellites repeatedly measure elevation and velocity. Radar maps fractures. Models are forced to reproduce not just where the glacier is today, but how it has changed over time. Every one of those measurements attacks a different uncertainty. How warm is the water beneath the main trunk? How does it circulate? How quickly is the grounding line moving? Which subglacial ridges are strong enough to slow retreat? Where is water stored beneath the grounded ice? How much does the eastern shelf actually buttress the glacier? Which satellite? Measurements produce models that best reproduce observed mass loss. And most important for the future, what combination of geometry and forcing would turn continued retreat into a much faster phase of ice loss? The 2026 results have narrowed some of those questions while making others more urgent. We now have direct measurements from beneath a part of Thwaites that had never been sampled that way before. We have seismic evidence that the bed is a patchwork of hard ridges, deep basins, wet sediments, and active water systems. We have model experiments showing that recent elevation changes can imply very high loss rates over the next several decades. And now we have a 3-model experiment showing that simply removing ocean melting does not send Thwaites back toward its old state. The warning is not that scientists suddenly discovered the glacier is big. They have known that for decades. The warning is that reversibility may be much harder than the simple story suggests. When people hear that warm water is melting a glacier from below, the intuitive solution is obvious. Cool, the water in the glacier recovers. Pine Island behaved roughly that way in the new zero-melt simulations. Thwaites did not. Its history and geometry had already moved it into a different configuration. That makes time matter. The longer a large ice system retreats, the more its boundaries, stresses, and exposure to the ocean can change. Some of those changes may be reversible. Others may not be reversible on timescales that matter to human societies. The scientific challenge is to identify which is which before the consequences are fully visible at coastlines thousands of miles away. And those consequences do not arrive as a single wave from Antarctica. Sea level rise raises the starting point for every coastal tide and storm surge. A few additional centimeters can turn a flood threshold that was rarely crossed into one reached more often. Larger increases amplify that effect. Over decades, communities respond through barriers, pumps, raised infrastructure, managed retreat, revised building standards, or some combination of them. Thwaites is one contributor among several, but it is one of the largest uncertainties because of the amount of ice connected to its basin and the possibility that its retreat could influence neighboring parts of West Antarctica over much longer timescales. That is also why the nickname Doomsday Glacier can mislead. It makes the story sound binary, intact, or collapsed, safe, or doomed. The real scientific problem is a continuum of rates, thresholds, delays, and partial commitments. Thwaites can be dangerous without disappearing this century. Its eastern ice shelf can fracture without instantly adding 65 centimeters to the ocean. A model can show unavoidable future loss without proving complete, irreversible collapse. And emissions cuts can still matter even if they cannot restore the glacier to its 1940s position. Those 4 statements are the boundary around the new warning. So what should we watch next? The first signal is the grounding line. If retreat accelerates into deeper inland terrain, especially along the major troughs mapped beneath the glacier, concern about sustained dynamic loss rises. The second is surface thinning and flow speed. Satellite altimetry and interferometry allow scientists to see whether inland thinning is spreading and whether ice is accelerating farther from the coast. Those measurements are especially important because the March study showed that surface elevation trends can dramatically improve how models reproduce observed mass loss. The third is the ocean beneath the glacier. The February drilling campaign demonstrated both how important those measurements are and how hard they are to sustain. Long-term records of temperature, salinity, currents, and melt would help distinguish short-lived variability from persistent forcing. The fourth is the bed. The new seismic map revealed features that can either resist or redirect flow. As the grounding line approaches, major ridges and basins knowing the exact shape and mechanical properties of those features becomes essential. And the fifth is fracture evolution in the floating ice. Not because one crack is a countdown to doomsday, but because damage changes stress transmission and can alter how the glacier interacts with pinning points in the ocean. None of those observations will produce a date circled on a calendar. That is not how this hazard works. The most defensible scientific picture in August 2026 is more sobering than a countdown and more useful than one. Thwaites is losing ice rapidly. Recent observations and models indicate that loss will continue. A new peer-reviewed modeling experiment says part of the current retreat cannot be reversed simply by eliminating ocean melt even over 150 years of an extreme hypothetical scenario. Separate 2026 work projects, the potential for much higher loss rates over the next 50 years, if observed thinning trends continue to shape the models. Field measurements confirm that relatively warm ocean water is reaching beneath the fast-moving trunk. Seismic surveys show that the bed beneath the glacier contains both obstacles and weak water-rich regions that current models still struggle to represent completely. There is no scientific basis for saying Thwaites will suddenly collapse tomorrow. There is a strong scientific basis for saying the glacier is already changing in ways that may commit the world to additional sea level rise, while the final amount remains sensitive to choices and processes still unfolding. That is what makes the new warning so important. The danger is not a movie-style instant collapse. It is a giant ice system carrying the momentum of its own history forward while the ocean keeps pushing from below and the bed beneath it decides how far, how fast, and in what form the retreat continues. At the edge of West Antarctica, the grounding line is invisible from the surface. There is no siren when it moves. No city sees the moment a ridge loses its grip beneath 2 kilometers of ice. But satellites can measure the thinning, seismology can map the bed, instruments can feel the warm water below, and models can test whether the glacier still remembers a shove delivered 80 years ago. The newest answer is yes, and that may be the most consequential warning Thwaites has given us yet.